Good afternoon, ladies and gentlemen. It's a pleasure to be here to talk to you today on some of what I consider to be interesting topics relating to water quality. And I'm a microbiologist by background, and I've been asked to talk to you today a little bit about microbiological monitoring, what it means, and perhaps when it's beneficial to do such monitoring, and perhaps sometimes to understand a little bit more about when you should monitor and how you should monitor. And I'm going to start at the end of my presentation and say one thing, which is that if you take one thing away from this presentation today, please let it be this, that the monitoring that you have to do for regulatory compliance does nothing whatsoever to protect public health. It's a regulatory requirement, but it does nothing to protect public health. That's not to say that monitoring can't protect public health, but the regulatory requirements, at least that you have, do nothing to protect public health. So we'll start a little bit, I'm going to start a little bit talking about microbiological monitoring per se, traditional monitoring, why you monitor, or at least why monitoring was first introduced, and kind of what that means and where you should be looking to do your monitoring today. So these are the traditionals, or some of the traditional waterborne pathogens that fortunately we don't see very often now being spread by waterborne routes. But certainly Salmonella typhi, the various types of Shigella, and cholera. At least in the Western world, we don't see too much of any of these being spread by water. They certainly still are, and we do see from time to time cholera outbreaks or pandemics across the world. But traditionally, we don't see them very often. They're not something that we consider to be now major causes of waterborne disease, at least in the developed world. And they tend to be also restricted to more tropical climates. But then we've got a whole bunch of new ones, and these are not really new. They've been around a while, and you'll be no doubt familiar with them. They're new in as much as they've come to the fore within the last 20 years or so as being waterborne diseases that we've understood a little bit more about how they're spread by water. And some of them, at least, we've only really begun to know that they cause disease within the last 20 years, particularly Cryptosporidium. But these organisms are the ones which now there's an awful lot of money being spent on investigating them, researching into them, trying to understand what they do and how they do it. Actually, most of that money that's spent researching these organisms, at least in as far as their role as waterborne pathogens, is pretty much wasted. We know they're there. We know how to predict when they're likely to be there. The money would be far better spent actually preventing people from consuming them. Cryptosporidium in the US, probably $50 million in the last 10 years on researching methods of finding it and understanding it, and is this strain the same as that strain? We're still no further forward. It doesn't help. The academics do well out of it. They fund their 3 months every year doing research, but in terms of protecting people, has it helped? No, not really. We're no further forward. And Milwaukee, where allegedly 400,000 people got sick and 100 people died, could happen again tomorrow, and it would be the same disaster, it would be the same disorganized mess. We still wouldn't know really what to do. So these are supposedly new waterborne pathogens that everybody's concerned about, if these are ever dealt with, there'll be another list of new ones. And trying to find methods of treating drinking water targeted at specific organisms is a crazy idea. It makes no sense at all. And hopefully, by the end of this presentation, you'll have a bit more of an idea why I'm saying that. But it's true that targeting specific organisms is not a smart way of spending your money. Consequently, monitoring for specific organisms is not a good investment, generally. We're all familiar with the concept of indicator organisms. This concept goes back a long way. When doing any kind of microbiology on water was pretty difficult. And the idea was to pick a group of organisms, or a single organism preferably, that can be used to indicate the potential presence of enteric pathogens. And when this concept was developed, the enteric pathogens we were talking about were things like Vibrio cholera, Shigella, and Salmonella. And initially it was coliforms. They were the initial indicator organisms. Well, I guess in truth, initially it was just total bacteria, but that's kind of not a very good indicator. And then we moved to coliforms, which is also not a particularly good indicator of fecal contamination. So some smart cookie came up with the concept of a subset of coliforms known as fecal coliforms. Well, you'll probably get by the end, or a little way further into this presentation, you'll probably get the impression that I don't really agree with the concept of fecal coliforms, because there is only one fecal coliform, and that's E. coli. And that's a specific organism, very well defined, both in the way that it behaves when you grow it, but also genetically, it's very well defined. And E. coli is a specific indicator of fecal contamination, and it's the only one that we can readily use that is a specific indicator. There are a couple of other things that you might say, well, you only find those in feces, but they're much, much harder to identify. So bear that in mind, that E. coli is a further subset of that mysterious group known as fecal coliforms. What are the characteristics of good indicators for fecal contamination? Well, whatever they are, they must be present in all feces. Good news is E. coli certainly is present in all feces. Should be there more in greater numbers than pathogens, and that doesn't mean individual by individual, because if somebody has an acute gastrointestinal infection, then the pathogen may actually be more numerous than E. coli. But if you take everybody in this room and collected their feces for a day and then enumerated, you would see that E. coli was more numerous than any pathogens that might be there. And incidentally, looking around, there's probably 5 or 6 of us that sometime today are going to excrete a pathogen, whether you know about it or not. Good indicators also should be able to survive for similar or maybe even longer periods of time in water than pathogens. Well, when we look at that for E. coli, it's probably true to say, well, it does for some. For the likes of Salmonella and Shigella, Campylobacter, yes, it does survive for similar periods or longer. The likes of viruses and Cryptosporidium and Giardia, maybe even Vibrio cholera, because it's one of its natural habitats is water, probably doesn't survive for similar periods. In most cases, it doesn't. And certainly Cryptosporidium will survive for up to a year. E. coli certainly doesn't hang around for that long. They should have similar or higher resistance to disinfection. The idea behind that is, well, if you're looking at disinfected water and you find E. coli there, then the likelihood is that you will also, if that's still there, then the likelihood is that pathogens will also still be there. And again, when you split the groups up, the traditional pathogens, E. coli, yep, it has similar or similar resistance to disinfection. But you look at the viruses and Cryptosporidium and Giardia, and no, it doesn't, has a lower resistance to disinfection. Should be easy to detect. And any of you that do testing for microbes in water, hopefully by now know that E. coli is pretty easy to detect. It's much easier than fecal coliforms, that's for sure, because you know exactly what you're looking. And there are commercial tests, and one of your sponsors at this conference, IDEX, makes the largest selling commercially available test for E. coli. It's simple to run, and I'm sure you've all seen it in the trade show. So E. coli does satisfy that requirement, that it's easy to detect. What can we say about E. coli as an indicator? Well, it's the best available indicator for traditional pathogens. And by traditional, I really mean bacterial pathogens. It doesn't correlate very well with the presence of viral or protozoan pathogens in raw water. So you can have pathogens there, Cryptosporidium, Giardia viruses, can be present in raw water in the absence of E. coli because they survive longer in the environment. So if you have a contamination event that occurs days before, miles away in a river, the E. coli may disappear, but the Cryptosporidium and Giardia viruses will still be around. So they're not good indicators. The presence of these newer or more newly recognized pathogens, but they are pretty good with bacterial. They're also not good indicators of the presence of viral and protozoan pathogens in disinfected water because they're more sensitive to disinfection than either viruses or protozoa. Or at least that's true of traditional disinfection. So what should you look for when you're looking for an indicator of fecal contamination? Should you use fecal coliforms or total coliforms or E. coli? Well, it's kind of a difficult question to answer in some respects, but one thing you can be sure about is if you are looking for a specific indicator for fecal coliforms, i.e. fecal contamination, then you should be using E. coli. Not this fuzzy group that we call fecal coliforms, because they can be either fecally derived or environmentally derived. They can survive and they can grow in the environment, and indeed they do grow in water distribution systems. And I know you have another presentation specifically on biofilms in this conference, and I'll show you a couple of instances of biofilms where fecal coliforms, or so-called fecal coliforms, have been growing in a distribution system and causing all kinds of potential problems, both aesthetic and health. And it's important to note that the presence of fecal coliforms in drinking water does not necessarily constitute a health risk. So if you're testing for fecal coliforms and you find them, the next question is, well, do they come from feces or not? And the only way to understand whether that's true is to check out whether they are E. coli or not. So in effect, testing for fecal coliforms, it's really a waste of time. It's a crazy step, because before you're going to do anything to understand whether that water is genuinely contaminated with feces, you're going to have to determine whether it's E. coli. So it makes kind of a lot of sense to just test for E. coli in the first place. It's also faster and easier. But it's not all good news, as these things seldom are. And as I said at the start of this presentation, monitoring for E. coli in treated water is more a regulatory tool than an operational one. When you take your one sample a month or one sample a week, whatever it might be, for testing for coliforms and E. coli, it's an absolute waste of time as far as protecting public health. When do you take it? What time of the day? You take it at the weekends? No, nobody ever monitors at the weekends because nobody gets sick at the weekends, do they? Plants always work well at the weekend because nobody's there to see that they don't, usually. Why do we test 100 milliliters? You know why? Well, because that was convenient. That was the volume that people could conveniently handle. If you increase that, as we have been doing in a recent study in Florida, and maybe you take 2 liters, right, so 20 times the amount, you know what? You tend to find coliforms and E. coli more often. So what does that mean? It's there in 2 liters, which is supposedly, if you believe this, you believe anything, but supposedly you all drink 2 liters of tap water a day. I don't know too many people that do, but those are the figures that are used for risk assessment and such like that. Everybody drinks 2 liters a day. Well then, if that's true, wouldn't you want to test 2 liters? Or maybe you want to test 20 liters or 200 liters. Or if we wanted to make sure everybody in this room wasn't going to get contaminated, maybe we need to test 20,000 liters. The point being that when you do that testing, you're only saying, well, in that 100 milliliters, we didn't have the target organism. So what? Doesn't mean anything. Even if it is clear, you don't find E. coli, it doesn't mean that that water's safe to drink. It's not necessarily free of viral pathogens, protozoan pathogens, because chlorine will kill off E. coli real quick. But it doesn't touch cryptosporidium, for example. You can drop cryptosporidium into neat bleach and leave it overnight, and it's still viable. So it's not telling you anything about the safety of that water. If you're concerned with meeting regulatory requirements, as obviously everybody needs to be, then you test 100 milliliters of water when you're told to, at the frequency you're told to, using the methods that you're told to, and submit the results. If you're interested in whether that water is safe to drink, then what you actually should monitor is not the bacteria that are present in the water leaving the treatment plant, but it's the way that you treat the water. So you should be monitoring your treatment processes, not the final product. The food industry has known this for years. Food industry does very little endpoint testing because it's a waste of time. Because they know that if they want to be certain that what they're putting out there is safe, they have to test all of it. And if they test all of it, they've got nothing to sell. So they quickly came up with a concept that if we monitor the processes that we know make our product safe, then we don't really need to do end product testing. We might want to do some raw materials testing, but end product testing, not really useful. A few smart people in the water industry are now coming around to that, and World Health Organization is now beginning to push that concept too, that end product testing doesn't actually help. The other thing that's quite important is that outbreaks have occurred, as you've already heard during this conference, where the water meets all the regulatory requirements. So Milwaukee, 400,000 people get sick. But we've got the tests, we've got the data here that says this water's okay. Meets all the regulatory requirements, it's fine. Well, the legal action's still going on, so over 10 years later, so the cost of that outbreak is enormous. Those indicators that we use for regulatory requirements only give a very, very small shot at what's really going on. So do them by all means, because you have to, but don't think, oh, we've got no coliforms, no E. coli, that water's great, because that's just not true. And I will show you some examples of what happens if you believe that. Okay, right, so anyone that's selling virus tests is not going to like me when I finish this slide. There are a few places around the world that will offer monitoring for viruses in drinking water. What do I think about it? Well, same as I think about most of the research money. It's waste of money, and it can be much better spent elsewhere. Why is that? Well, there are a lot of viral species that have been shown to be waterborne. A lot. The tests are pretty much specific for each virus group. So you'd have a test for rotaviruses, and then another one for Norwalk viruses, and another one for adenoviruses. Which one do you choose? Which group do you want to look for? You know, we want to look for all of them. Then probably you're going to have to sample, I don't know, 20,000 liters of water, and it's going to cost you, yeah, probably about $20,000 per sample. And then when you get negatives, what does that mean? Because the sensitivity of those tests is very variable. Sometimes you get very good recovery and efficiency in detection. Sometimes it's less than 10%. You want to spend $20,000 on something that 9 times out of 10 is wrong? Doesn't seem like a good use of resource to me. The other point is that there aren't tests for all the viruses. So you can only test for a certain group, and the others you can't test for anyway. So really, even if you're concerned about viruses, actually testing for them is not going to help you an awful lot. What about protozoa? Well, a lot of people have got rich on protozoa in the last 10 years, that's for sure. Should we be monitoring for them? Well, if you believe the UK government, you need to monitor every surface water plant that might be at risk every day, a minimum of 22 hours a day. You need to be sampling. If you believe US EPA, well, no, you don't want to do that treated water rubbish, but you need to sample once a month for 2 years. I don't know what that tells you either. It tells you 24 snapshots, you've got Cryptosporidium there or you haven't. And we know these bugs occur in clumps. So they'll come through at high numbers for a short period of time, then there'll be nothing. So routine monitoring generally is not recommended, apart from by a few regulatory authorities that really are recommending things that are pretty dumb. Tests are expensive. What would you pay typically? Probably 500 Canadian, something like that, for a single test. And yet again, recovery efficiency is variable and often poor. What that means is sometimes you might get an answer saying there's nothing there. Well, the reason there's nothing there is because the lab wouldn't have recovered them if they were there, because the test is quite difficult to do. How variable? Well, there's a lab in the US that probably would like to think it's the best protozoan lab in the country, maybe in the world. Knowing the owner, probably she thinks that. But we know from some specific tests that we did that the results, even from a lab that probably is pretty good, are very variable. So 8 samples that we submitted to that lab that were run at the same time, so on the same day, by the same person with the same reagents, and they were all exactly the same, the recovery was between 7 and 71% on those 8 samples. So we gave them samples with 100 oocysts in, and one time they only recovered 7 of them, another time they got 71. So the test is very variable. When you find them, should you find them, are they organisms that are going to cause a problem? There are a lot of Cryptosporidium out there that don't infect humans. Do we want to know about those? Well, maybe, depending on the point of the reason that you're testing, but a lot of the time, no. And most of the tests don't distinguish between live and dead. So what does that mean? You know, do you want to know about dead bugs in your water? Well, I can tell you that if you monitor finished drinking water at virtually every drinking water plant in the country, with possible exception of membrane-based plants, but virtually every other type of treatment, if you monitor the finished drinking water for dead E. coli, you'll find them. So do you want to know about dead crypto? Not really. But if you do, $500 a shot, and I'll be happy to arrange it for you, for a commission. So what should we do about protozoa? We know that they are important. We know that people get sick. And we also know that there's a typo on this slide, but I'll point it out to you before anybody else sees it, and perhaps you've already seen it. That should say multi-barrier treatment. What should we do about assessing the threat from protozoa? You want to know, at least I would hope you'd want to know, whether or not you have a potential protozoan problem. So catchment assessment generally is the first step in assessing that threat. And for some catchments, not many, especially these days, it's pretty easy because you can assess the catchment and say, nah, there's no threat. The only time that you can do that is if you have either a completely secure groundwater and you can be guaranteed it's going to remain that way, then you're not going to have a crypto problem. Or if all of your water is from a desalination plant, then you're not going to have a crypto problem. Other than that, you will have some threat based on your risk assessment. And the risk assessment I'll talk about a little bit more in a moment, but during that you assess, firstly, how likely is it that our raw water is contaminated? Then you've got to look at what treatment do you have. And as with virtually all microbial threats at least, multi-barrier treatment is the way to go, always. There are no exceptions. You should never rely on a single barrier. When you do, you get all kinds of problems, and I'll be talking about a multi-million-dollar problem in Australia in a while because they didn't have multiple barriers. Once you've got them, great treatment plants, there's lots of them out there, fantastic. Don't they look good? Cost millions of dollars to build. Not much good if you don't operate them properly. You can have all the technology you like, but if you don't actually monitor that it's working and adjust it when you need to, you may as well just drink the river water. It's the biggest cause of waterborne disease is improper operation of treatment facilities. No doubt about it. And there is waterborne disease, by the way, going on every day in virtually every community. We may not see the massive outbreaks like Milwaukee and such like, but sporadic waterborne disease occurs every day in virtually every community. So now you've understood what the risks are in your raw water. You've got a fantastic millions of dollars invested in treatment technologies, and you're running it properly. Then you need appropriate monitoring to demonstrate that you're running it properly. Now I'll go back to testing for E. coli or coliforms or fecal coliforms or whatever in treated water. That was the initial attempt by sanitary engineers to say, is the person that's operating that facility disinfecting the water enough? That's what they did to check, because it wasn't easy like it is today to monitor chlorine levels constantly. So they used a bacterial indicator system. Nowadays, you don't need to do that. Everything's online. You can do it all instantly. Do you want to know that you drank water yesterday that was contaminated? You're going to get sick tomorrow? Nah. Much rather know that what I'm going to drink has already been tested, and we know that it's been disinfected, and I'm going to be fine. That makes a lot more sense. So appropriate monitoring means online monitoring, wherever possible. And when it's not possible, well, then you may have to do some other things. You may have to do a few manual tests, but do ones that take minutes rather than days. Nobody wants to know the reason why they got sick. They want to know that they're not going to get sick. So appropriate monitoring is what you need. Catchment assessments. Well, who's got a surface water plant that one of these doesn't impact on? I don't know of any. You've either got sewage effluent or septic tanks or farming. And if you haven't got farming, you've got wild animals, and then maybe you've got some degree of human activity, even if there's not a lot. It takes one sick person, by the way, to be in a catchment. And if they're sick, sometimes when you've got to go, you've got to go. And that's 10 to the 9, 10 to the 10 crypto. That's a lot of crypto to get rid of. So any surface water catchment that I've ever seen has at least one of these things going on, which means you've got a risk. Now, the more of those that you have and the size of those will affect the severity of that risk. So if you've got sewage treatment plants and septic tanks and farming going on, you've got a huge risk. And I'm glad to see that Canada's actually beginning to just put out a call for proposals to try and develop something that will look at this kind of stuff for not just for drinking water, but for recreational water as well, and agricultural water. And it's encouraging to see. It'll be even more encouraging if they give me the money to do it, but it's encouraging that they are going down that road, that's saying, well, assessing what's in your catchment is really important. And believe me, it is, because if you don't do that, you don't know how big the risk is, and you don't know how much you need to spend, and where to target the limited resources that everybody has. But when you do this kind of thing, this is part of a list actually taken from some regulations in Scotland that say, well, if you have sewage effluent in your catchment, then score it 6 points, and if you have septic tanks, that's another 4, and if you have farm animals, it's another 6. Well, doesn't it matter what size the sewage treatment plant is, and doesn't it matter how well it works? If it overflows every time it rains, it's much more of a risk than one that's got UV tertiary treatment on the end. So if you're doing a risk assessment for whatever, whether it's for protozoa or whatever, do it as well as you can do it, because it really is worthwhile information. Having done all that, then let's look at multi-barrier treatment. Amazing to think that some regulatory authorities don't think that treatment steps are cumulative. They kind of treat them separately. Well, no, if you're taking out 2 logs at the beginning and then you take out another log, you're taking out a log of an awful lot less than were there originally. So they are cumulative. The more treatment steps you have, the better the removal. Hence, the better the treatment. Most of the time, do you need multiple barriers to protect you? No. Most of the time, single barrier will do the job. Most of the time. But what's most of the time? 51% is most of the time, isn't it? Multiple barriers really represent insurance against the failure of any one of the other barriers. So if you're relying on a single barrier and that one fails, then you're in trouble. As 3 million people were in Sydney in 1998. If, however, you've got multiple barriers and one of them fails, well, the other 2 will pick it up. They may not produce quite as good quality water at the end of it, but you will have removed the majority of what you're trying to remove. So think about multiple barriers as insurance against failure. And believe me, failure occurs regularly, especially in those plants where you don't bother to monitor whether your plant's working or not. It occurs much more frequently than people think. Coagulation losses occur. Breakthrough in filters occurs. Often. So the bottom line is that several barriers with partial removal has got to be a better bet if you're constructing a plant than a single barrier with absolute removal. Because nothing's absolute. You can have a membrane plant, one fibre breaks and the bugs are through. May not be that many, but some of them will get through. So, and if you have a catastrophic problem and a lot of fibres break in a membrane plant, then you're really in trouble. So multiple barriers, definitely the way to go. Even if each of those barriers is not anywhere near absolute, it's certainly preferable. And we will come back to that because it's kind of a little bit of a hobby horse of mine, I guess. What about operating them then? Well, you know what? Isn't it amazing how water treatment plants, most of them, they're manned from like 8 in the morning till 5 or 6 in the afternoon. And then everyone goes home and they operate perfectly for the other 14 hours, don't they? Hopefully. Well, reality is that most of the problems that occur, that develop into water quality incidents, occur outside of that 8 to 6 working day period. Water treatment plants require constant attention, and the bigger and more complex the treatment plant, the more attention it needs. No question. But there's very few water treatment plants that are actually manned 24 hours a day, and probably rightly so. But there are things you can do at least to alert somebody that your treatment plant is failing. It's no good going in at 8 in the morning and finding that since you left at 6 o'clock the previous day, you've just been pumping out raw water for potable purposes. They do require constant attention. What if the raw water changes? Often does. Doesn't need much of a change. Might be a turbidity change, might be an alkalinity change. Anything that makes the treatment of that water or the treatability of that water change is important. If the raw water changes in any way, you need to change the way you're treating it. How do you know that if you're not monitoring what's going on in the raw water? Tough one if you're not there. Very tough one. You have coagulation going on in your treatment plant. How often do you check that you've got the right coagulant dose? Years ago I worked for Thames Water. It's the third largest water company in the world. And when I was auditing some of their plants, it's like, well, what coagulant dose do you use? And they have one coagulant dose that they use for 6 months, and then it changes for 6 months. On October the 1st, we change the coagulant dose to this, and it'll always work. Crazy. The coagulant dose you need varies maybe daily, depending on what your water source is. You need to do regular checks on what coagulant dose you need. What about the filters? Oh, well, we backwash them every 24 hours, whether they need it or not. That's the normal. Well, what if they need it at 18? Well, we do it at 24, because that's efficient, or it's cheaper. Yeah, and people might get sick. How often you backwash your filters depends on how good your filtration is actually working, depends on how good your coagulant is working, depends on your raw water quality, it depends on a whole bunch of things. So to say we do it every 24 hours, mad. It's nuts. Absolutely nuts. But that's what most people do. They don't measure head loss or how efficiently that filter's working. It's just like, well, we'll do it every 24 hours. Or if we can save a bit of money, we'll do it every 36, actually, because it's cheaper. Bad. So you need to check each of the processes all the time, as often as you can. You need to know about your raw water quality. What's the turbidity like? What's the alkalinity like? Who measures alkalinity in raw water? Well, anyone that's doing coagulation ought to be, but they don't generally. What's the pH like? Just what does it look like? Sometimes you talk to operators of treatment plants and they just look at the water and say, this is going to need such and such, and they're right. Because they know from experience that when the water goes to this color or has this particular characteristic, it needs this type of treatment. You need to look at what you're treating and treat it appropriately. Do jar tests for coagulant dose. They're not so tricky. They're pretty easy. What about filter performance? Well, that's always an interesting one. Now, just measure what's going out. Now, I know in most situations we're talking about small treatment plants here, but large treatment plant, multiple filters, and they measure the turbidity of water going out to the community. Doesn't tell you anything, because if you've got 16 filters, you might have 15 that are doing great and one that's not working at all. You won't notice it if you only measure the final turbidity. So measure the individual filter performance. And don't just measure turbidity either, measure turbidity removal. Not too many people have cottoned on to that, but you know what? If you've got raw water coming in at 1 NTU, it's much easier to get to 0.1 at the end than it is if you've got raw water coming in at 100. Like 2 logs more. So you want to be looking at turbidity removal at each of your processes. And we all measure disinfectant residual. Yep, got to be there. How about measuring disinfectant demand? How many people actually do that? Not too many. Very important. If you don't do it, you don't understand what's hitting your disinfection system, and then you don't understand how well your disinfectant is working. You also don't understand how long it's going to last, or whether you've got all kinds of bugs in there that are being protected by particulates and organics. Better get moving, I'm running out of time here. Developing criteria for monitoring treatment plant performance. Well, it's got to be based on risk assessment, and you prioritize your risks to public health. So what are our major risks based on our raw water and the community we're serving, et cetera, and that's where you start. You've got to develop surrogate criteria for monitoring treatment plant performance, and that's what I was saying. You test real time wherever you can, or quick tests, not wait 2 or 3 days for a lab analysis. That doesn't help. So it's got to be real time wherever you can. And imagine cryptosporidium. You're gonna wait for a cryptosporidium result to know whether you've removed it? Well, Ask that to anybody that's had a transplant or has got HIV or is any way immunocompromised. They want to wait 3 days before they can drink that water. No, they want to know that you've treated it properly. The performance of your treatment plant, you should base it on risk removal. You know what the risks are. That's why I said you need to put as much effort as you can into determining the risks and quantifying them. And then you can measure your treatment plant performance based on the risk removal. And you know what? If you look after more than one plant, you've got to do it all over again because the plans are specific for individual treatment plants. So if you've got coagulation, you must do this. Jar testing is dead easy. It's very, very important. If you screw up the coagulation, all kinds of other things can go wrong. And there you can see what happens. With different coagulant doses, this is what you can see, different amounts of turbidity removal. You know, if you're too low, you're not removing it. And one of the points that most people fail to recognize is that too much coagulant can be almost as big a problem as too little. So you want to get it right. Use the right amount and the right type of coagulant. You know, ferric doesn't work for everybody. Alum doesn't work for everybody. Poly doesn't work for everybody. You've got to choose what's going to work best for you. Let's talk about Sydney, because that was, I enjoyed my time down there. 4.5 months in Sydney, investigating what they did wrong. It took about 4.5 minutes, actually, out of the 4.5 months. But they paid the company I was working for about $500,000 for me to do it, so I guess that was a pretty good rate for 4.5 minutes. Just a little bit of background. Prospect Water Treatment Plant supplies water to 3 million people. It's run by a French organisation, not that I got anything against them, but they're private, and their primary concern is making money. They have a raw water storage facility where, when it's full, stores enough water for Sydney's demand for 7 years. Now, on the basis of that, they made a pretty dumb assumption. That was, well, we've got all that water in there, so it's going to be consistent water quality. It's reasonable to think that if you understand everything about what's going on in that storage, and they clearly didn't. But we'll get to that in a minute. On the basis of that, they said, well, consistent raw water quality, what can we use treatment-wise to treat this water as cheaply as possible? Because that's all they're interested in. You know, they get paid by per cubic meter. So they said direct filtration, no problem. So water comes in, you throw some coagulant at it, and it coagulates on its way to the filters, and then the filters deal with it. Fantastic. And then chlorine disinfection, out you go, everything's great. Well, I guess it's an improvement, because Sydney, up until this plant was built, which was not that long ago, had no water treatment at all, apart from a little bit of chlorine. 3 million people. Bit scary, but there you go. They only got this kind of at the last minute. It was like government was just about to chop it, and they squeezed it through. Incidentally, the direct filtration that they developed for this plant, when it was going out to bid, the media that they used failed to meet the treatment criteria, but they still got the contract. Who knows how that works, but they did. Consequently, sooner or later, you're going to have a problem, and they did. 3 separate incidents occurred over a period of 3 months. 3 million people boiling their water. It was administratively a complete disaster. They completely screwed it up. You had the health department say boil, and Sydney Water saying no, and then vice versa, and it was on TV and the newspapers, and there were guys saying, but there's no crypto there anyway. And then 2 days later, he signs a statement saying, there's definitely levels of crypto in this water that are of human health significance. It was a complete disaster. Starting with, how did they find it? Well, they had a monitoring plan. It's a good idea. unfortunately included taking samples from the distribution system. And that's always a pretty dumb idea if you're going to treat them with any degree of seriousness, because when you start to look in distribution systems, you find all kinds of inanimate objects and things that have been there for years. And these crypto, virtually all of them that we saw at the beginning were dead. They've been there for years. They found a single oocyst, and then they said, we better sample a bit more, so they sampled a bit more and they found some more. Not too surprising. And eventually they got to a position where they found out it was the treatment plant. But actually it was a real coincidence that it happened. You know, they could have found that oocyst at any other time and they wouldn't have had it wouldn't have been a genuine problem. But as luck would have it, that's what happened. So Prospect Water Treatment Plant, as I said, run by external contractors, and during the time that we were finding like 1 oocyst per litre or a few in every 10 litres at least, the contractor said treatment plant's performing normally and within specification. The final water turbidity, this is the one at the end, you know, where it's all mixed, right, every filter, less than 0.1. It's 0.5 coming in, but, you know, but it's all performing really well. No coliforms or E. coli. Yeah, so the chlorine's okay. But they did have some maintenance underway on the final water tanks. And this is the beast. Microbiologists can never resist putting these things in, can they? But this is the beast that caused the problem. This is an EM of a Cryptosporidium oocyst. That's the thing that all that money's been wasted on. So what happened in the first event? We found parasites in the distribution system. And despite the fact the contractor said everything's been going just fine, we've been supplying water to you that's just perfect, so all within specification. Except they lost coagulation 4 times during a 5-day period. It's not such a big problem if you've got a conventional treatment plant. It's a huge problem if you've got inline filtration, direct filtration like this is. Because what that means is if you lose coagulation, you're actually putting raw water onto your filters. What happens then? Well, because you're not coagulating, you've got lots of small particles. And that beast that we just looked at is a small particle. It's 5 microns. So the filters may have been working great for 18 hours, taking out all those crypto, they're all stuck in the sand, and then suddenly you hit it with raw water, and it has a lot of 5 micron particles in, strangely enough. And when you put 5 micron particles on the top, what you push out the bottom is 5 micron particles. So as soon as you lose coagulation, all those crypto that you've taken out for the last however many hours just get pushed straight through and into distribution, and people get to drink them. So if you lose coagulation on a direct filtration plant, your one and only barrier has just gone. Not only has it gone, but all the ones that you've taken out for the last however many hours, you decide you're going to give those to people for free. So single barrier, you know, for 3 million people, you're going to have a plant with single barriers? No, madness. It's madness if it's 30 people. But for 3 million, it's complete insanity. However, what else happened? There was parasites in the bottom of the final water tank during cleaning. Well, do you know how they got there? Because they didn't bother to look at their coagulation. And if you don't look at whether you're adding the right amount of coagulant, what happens is you get secondary coagulation. So after you've coagulated, it goes through the filters, you've still got the chemicals there, then you go into holding tanks before that stuff goes out, and the coagulant carries on working, and it will take out some more particles. And it did, and it does, you know, and in those particles were a bunch of crypto and giardia. When they cleaned that tank out, they washed a load of that stuff straight into distribution. Still didn't find any indicators, and still the final water turbidity was less than 0.1. Not much real satisfaction for people that got sick when you say, yeah, but everything was okay. And believe me, by the way, maybe those of you that are familiar with Sydney will say nobody got sick. And it was a laboratory stuff-up. That's the classic that one particular person in the US comes up with, who wasn't even there, incidentally, for 90% of the time. People did get sick, and it wasn't a laboratory stuff-up. Let's be clear about that. So, what happens with coagulant loss? Loss of coagulant can occur very rapidly due to relatively small changes in raw water quality. It does. As I've said, direct filtration relies almost exclusively on good coagulation performance, and if you lose coagulation, you push everything, all the smaller particles in your filters, straight through. Not a good scene. If your filters are working well, they've captured all the crypto and giardia. You lose coagulant, push them straight through. I'll say again that it's reliant on good coagulant performance, and therefore you must optimize coagulation. You know, these dumb ideas of, do I change it every month or every 6 weeks or every week even? It's not good enough. Unless your raw water source is really consistent, that's not good enough. What happened in the second event? Well, that reservoir that I told you that could contain 7 years worth of water for Sydney was half full. And then it rained. And it filled up in 7 days. Filled to overflowing. So there was a heap of rain. It was wet. And the water entering the reservoir was colder than the water that was already in the res. So it was denser. So when it flows in, it just goes to the bottom. And it had washed off, they'd had like 5 years of drought or something in Sydney, so it washed off all this wild animal fecal material, sewage sludge that had been sprayed in the catchment, all kinds of stuff, washed down into the rivers, carried along into the res, dense, hits the bottom, goes along, and hits the ball at the far end and goes up to the abstraction point, and you've just taken out this nice cryptosporidium soup, which had low turbidity and very low alkalinity, because it's rainwater mostly, and huge numbers of crypto and giardia in it, huge numbers. And you know what? Those huge numbers were pretty much the same coming into the plant as they were going out of the plant. Very little difference. Why is that? Because they couldn't coagulate it. Didn't matter because it was low turbidity. So they said, well, you know, it's good quality water going on the filters. Doesn't matter if it's not coagulated that well. We don't care. We're still getting paid. Low turbidity does not mean there aren't any parasites there, whether it's in raw or treated water. Okay, so raw water, people have this strange idea that if raw water has high turbidity, then it's got bugs in it, and if it's got low turbidity, it doesn't have bugs in it. Not true. Clear, low turbidity waters can often have much higher microbial loads than dirty waters. Depends on what the source is. Bugs don't have, you know, you can have a heap of bugs. You can only see, did you know you can only see, if you're very good, you can see 10 to the 6, a million bugs per mil. You can just see slight haziness. That's an awful lot of bugs. Do an awful lot of damage with 10 to the 6 crypto, for example. And if it's viruses, well, you can't even see that, you know, I mean, you just can't see them. So low turbidity, either raw or treated water, doesn't mean no pathogens. And same thing again, uncoagulated water, low turbidity, contains many small particles, cause shedding of the filters. That's what happened, and the bugs just went straight through. Third event, a little bit dodgy, this one. I don't want to say too much about this because I don't really understand it anyway. But there are 6 plants in Sydney. This one that treats water for 3 million people and 5 others. And they all went positive on the same day, which is a little bit worrying. But during that time, combined filtered water turbidity was less than 0.1, no indicators present, and high numbers of parasites. When I say high numbers, we got up to about 5 per litre on some occasions. That's a lot. Infectious dose is probably 5 or less. Let's just talk about a few of the assumptions that were made in Sydney that were pretty dumb. 7 years storage of water would result in poor water being diluted or aged before treatment. Yeah, if it all comes in at a steady rate and it's all the same temperature and it all behaves the same way, that's what will happen. When it absolutely pours with rain in winter, the water's cold, doesn't happen. Large storages result in consistent raw water quality. Well, since then, they've spent about $20 million putting in baffles to actually stir the water up so that you get mixing. You don't get a thermocline. Because large storage doesn't result in consistent raw water quality, not unless you artificially mix. Consistent raw water quality means checks of coagulation are not required. Well, I don't think they'd say that now. Strangely enough, they do jar tests at least twice a day now, I think. And low turbidity means no pathogens. You know, it's clean water coming in, it's fine. We're okay. It doesn't matter if we don't treat it. Dumb assumptions. So what are the lessons you can learn from that? Well, firstly, don't be in charge of a plant serving 3 million people. That's not a good place to be. Single barrier treatment's inadequate. And if it's inadequate for 3 million people, it's inadequate for 300 or 30. You know, if you're going to treat it properly, whether it's 3 million people or 3, it doesn't matter. Otherwise, just don't bother. Even with large storage capacities, raw waters can change rapidly. Most people don't have large raw water storages. Most people, are be abstracting direct from the river. Raw water changes real quick then. Measuring the turbidity of combined filtered water is misleading. It's not only misleading, it's pretty stupid. You measure the performance of each individual filter. Low turbidity water contains pathogens. Please remember that. Doesn't matter whether it's raw or finished. Just because you've got low turbidity doesn't mean it's pathogen free. And the thing I mentioned earlier, turbidity removal and not absolute turbidity is a surrogate for pathogen removal. So if you've got 0.5 coming in and 0.1 going out, you're not doing a very good job. So it's removal at each stage, not just the final turbidity. That's important. What do we conclude from Sydney? Well, direct filtration was unable to deal with rapidly changing raw water quality. Even if the operators had been paying attention, which I personally don't believe they were, I don't think they could have dealt with it. It's not a good system. Apparently functioning, the plant was apparently functioning well, but we still had large numbers of parasites leaving the plant. That can happen. It did happen. So don't always be reliant on final water turbidity, I guess. And investigation of the plant suggested some filters are allowed to assist the pass. Well, yeah, if you're not coagulating the water, you're going to. The turbidity might still be low because you're taking the rocks and the boulders and all the huge stuff out, but 5 micron particles are just going through. These are my opinions about Sydney, by the way. Most of them are in the report of the official inquiry. In this Florida system that's kept me away from this conference this morning, frequent coliform detected in water within the distribution system, like 1 in 5 samples going positive. It's a little bit more than the 5% they're allowed within the regulations. Occasional E. coli. They could reduce the occurrence of coliforms by flushing. Interestingly, coliforms were there even when the disinfectant residual was high. It's quite typical of a biofilm. And after flushing, the bugs reappeared. Where'd they come from? Well, the water has a high temperature, high organic load, and has a long residence time in the distribution system, like 8 days or something. Perfect conditions for bugs to grow, basically. And the distribution system was apparently colonized with biofilms containing coliforms. As you'll see, it definitely was colonized with biofilms. And as I said, the coliforms were present even when the disinfectant residual was at target levels. And it's a chloraminated system. Target level was about 4 ppm. And they were right up there, and they still had coliforms there. And flushing didn't completely remove it. This is a sample of the water. Beautiful stuff. This is drinking water. This is out of a 36-inch main, supplying a large part of a particular county in Florida. Wouldn't you love that to come out of your faucet? Beautiful stuff. And that's resulting from biofilm sloughing, caused by a change in the water quality going in there. This is in a zone where it's fed with both groundwater and surface water. And there's an interface zone, kind of fluctuates up and down depending on how hard the groundwater stations are pumping. And when you change the water quality, you change the characteristics, and the biofilm all falls off. This is what you get. Good stuff. I talked before about 100 ml samples versus larger samples. Well, when we looked at the treatment plants supply in this area, if you took 2 litre samples, you know what? We started to find coliforms regularly. Every few days we'd find them. Disinfection criteria at both the surface water plant and the groundwater plants were being met. There were relatively high numbers of particulates in those waters, particularly, as you will see from the groundwater plant, where there was a hydrogen sulfide removal tower. And organisms were being protected from the disinfectant by those particulates, and the distribution system was constantly being seeded. There's also a desal plant, and you can see this membrane's nicely fouled here. It's the back side of a desalination membrane, and there's biofilm growing on it. Happens. Any membrane will grow biofilm if you don't clean it frequently enough. It just washes into distribution. This is my favorite. This is biofilm. Bugs growing in a hydrogen sulfide reduction plant. So this is just a scrubber to get rid of the H2S because it's groundwater before it goes out to distribution. So it's all been treated. It's even been disinfected. Then we put it into this, and we run treated water through this stuff, and then pump it out and say, get on and drink it, guys. And it's full of coliforms, that stuff. Absolutely full of them. There's another pretty little picture showing biofilm here on a distribution pipe. That's a coupon taken out of a distribution pipe down in this area, covered in biofilm as well. How do you resolve that sort of problem? Get rid of the rubbish that's in your water, basically. Get rid of the particulates, reduce the organic load, and cut down the amount of time it hangs around. If it hangs around for 8 days, it's got a lot more chance to grow biofilm than if it hangs around for 4 days. So those are the things that need to be done. This is why I really put it in about the Florida situation, knowing that you were already going to have a talk on biofilms, but this is why I put it in. These are the lessons to be learned. Monitoring with 100 ml samples does not ensure the absence of coliforms or any other bugs. As I said before, they're for regulatory purposes, and it keeps a bunch of office wallers in a job, showing that you've got 0, 0, 0, 0 all the time. Negative samples do not mean that the bugs are absent. And if you want your disinfectant to work properly, then treat the water properly. Get rid of the things you're supposed to be getting rid of, the particulates and the organics. Just a couple of other quick things. Viruses and parasites in groundwater. These are kind of more just a few factual slides rather than my storytelling. Both of these types of bugs survive much longer in the environment than most bacteria, certainly than coliforms and E. coli. Viruses are smaller, so they might travel further. There are heaps of reports now where pathogenic viruses have been found in groundwater in the absence of coliforms, and similarly, most outbreaks of cryptosporidiosis, in fact, have occurred associated with groundwater don't have coliforms present. So, just testing for coliforms doesn't necessarily do it. If you want to protect your community against microbial threats, well, you can hire me and I can do all these things for you, but that comes kind of expensive, so I'd do it myself if I were you. Firstly, understand the threats to the raw water quality. This is all that stuff I talked to you about before, what's likely to be in there. Try and do it as best you can, quantify it. Then understand what kind of treatment you've got and what's the capability. Now that's pretty easy to work out. If you've got this many coming in and your treatment's only going to take out this many, then the difference between the two is what's going to go out to the population. Is that acceptable? Usually if you can measure it, the answer is no. If you can measure what's likely to go out, then usually that's not acceptable. Monitor the performance of your treatment processes. I know I've said this repeatedly during this talk, probably because I believe in it, probably because it works. You need to do it. You need to check constantly that your treatment is actually working. And also make sure you monitor the water quality and distribution. Going back to that raw water quality, identify the sources of pollution, and if you can stop them, stop them. Do whatever you can with real-time tests to monitor changes in physical characteristics of raw water. Understand what happens when the climate changes, when it rains, when you get snow melt, all that kind of stuff. What does that do to the raw water quality? Low alkalinity, generally, more difficult to coagulate, bit of a tougher job to treat, usually. Be aware of unusual events, spillages, that kind of stuff. What can happen? It's amazing the amount of time when a spillage occurs and people go, well, I wonder what that is. Whereas if they knew what was going on in the catchment, they'd have a pretty good idea what it was. So understanding the capabilities of your treatment process, it's all stuff I've said before. No single process will protect against all microbial threats. You must go for multi-barrier approaches. And one barrier is protecting your catchment. That's a barrier. The efficiency of your filtration and disinfection is dependent on your coagulation. I hope the message is getting across that coagulation is kind of important. Get it right, otherwise you're wasting your time. And the coagulation and disinfection performance are dependent upon a whole bunch of different factors. So you need to check regularly that it's working. When you're monitoring the treatment processes, check your coagulant dose with jar tests. As I said before, too much coagulant is almost as bad as too little. You must monitor individual filters and monitor disinfection demand as well as disinfectant residual. And I know this is all stuff I've said before, but I'm trying to summarize the main points for you. Remember this. As soon as you finish treating that water and you put it out in those pipes, the quality starts to deteriorate. And the longer it's out there, the worse it gets. And if you don't treat that water as well as you can do, then that deterioration is going to happen faster. Disinfectant residual can disappear real quick for a whole bunch of reasons. Dirty distribution system, infiltration, all sorts of things. Be aware of that. If you get infiltration, you've got low chlorine residual, you could be reintroducing pathogens, and with low, not necessarily only low disinfectant residual, but anything that promotes biological regrowth will lead to poor aesthetic quality. Last slide, I'm sure you're all glad to hear, and I've overrun my time, but never mind. It means that you can ask me fewer questions. Ensure that your good water quality is maintained from the source to the tap. So too many people just think about, well, it comes into my treatment plant here and it goes out there and that's all I'm concerned about. Embrace the whole idea, what's your raw water quality? And do you care about what goes out of your treatment plant, or do you care about what somebody's drinking? It's what they're drinking that's important. So think about the whole thing, source to tap. Protect your source. Do what you can to stop people throwing rubbish in it. Educate agricultural workers, educate industry, whoever you need to fix up the raw water quality, and make sure that when you finish treating it, it stays good because it's in good pipes. The protection of your raw water quality is paramount, but I know it's not always possible. But what I can tell you is there's always something you can do to improve it. And it's a pretty emotive subject. You start telling people, well, that guy up there is the risk. That farmer up there is the guy that's causing us problems and you as a community problems. So what can we do to get him to toe the line? There is always something you can do to improve the raw water quality. Please remember, multi-barrier approaches are always safer than single. Doesn't matter if it's UV or membranes or whatever. If you've got multiple barriers, it's always going to be better. Always. And finally, production of potable water doesn't end at the treatment plant. Remember, it's the stuff that they're drinking that really matters. On that note, I'm going to end, and I've managed to leave myself no time for questions, but I'm sure if there are any, we can squeeze a little time, and I'd be happy to try and answer them. Thanks for your attention.